Okay, welcome to the intro to the organic synthesis part 2. Last time we saw how you try connecting the simple reactions in order to synthesize a final product. So 3 types of approaches with the 2 reagent in the reactant side, and then you use a mechanism skill to deduce the product out of it. And type 2, you have reactant and product partial informations. Then you go like compare the two, come up with the changes. Then those changes you connect it to the typical reactions you remember: substitution, elimination, rearrangement, and addition, and all the details. Then based on the product, without any information in the reactant side, you do retrosynthetic thinking by disconnecting certain bond. So besides the retrosynthesis, in organic synthesis, you need to know the selectivity versus reactivity. So when you study each mechanism and simple reaction, you need to have a separate idea about reactivity and selectivity. So one of the first thing we have covered is when you have alkane like this, for any reaction you are required to have a leaving group. So when you need to have a leaving group here after your analysis, then you should know what reagent you use here to put leaving group there. Sometimes you need leaving group here. I mean, it really depends, but let me put one more carbon here, then it becomes more legitimate example. I know this drawing is ugly, but that's my fault, I'm sorry. So, you know, to put the halogen on the most substituted, you always need to try with the bromine, right? Bromine with the heat or light. If you attempt to put on the less substituted one, chlorine is useful, but you have to really calculate. If you don't like it, you go to the elimination, make double bond, then go anti-Markovnikov addition if the number of hydrogen versus reactivity of the halogen doesn't work out for you. In this case, it doesn't work out. It works for the primary. So chlorine will eventually go to the primary, I guess. So for this one, make the first, make double bond, then do anti-Mark addition. Yeah. So the kind of selectivity you need to consider. Let me change the pen. That when you have 2 different leaving groups, right, like this, and you have this reagent, you are set for SN2. Basically, you have leaving groups and you have a strong small base, and the leaving groups are on the small primary carbon. So both are good. If you have only 1 mole of it, where would you have a more attack, basically? Then the selectivity is going by the better leaving group, right? Because the leaving group is the product that needs to be more stable, and the bromide ion is more stable than chloride ion. So you end up attacking there more frequently, and then you get this product. So that's the chemoselectivity you need to know. And there would be case you need to know this aspect. Say you have a same leaving groups but one is on the primary, the other one is on the tertiary, and you're looking at again bimolecular reaction, then obviously this prefers primary with a less steric hindrance, so the activation energy is low here, so you attack there faster and you end up having Br with a 1 mole of methoxide. So the background of this is obviously when you have same reactant but two choices, right? You rather have more stable product because that's usually more going over a more stable small activation energy, thus it is faster. So more exothermic, giving you more product, small activation energy, faster kinetic controlled product you get. Sometimes the steric changes everything. So starting from same reactant, you have more stable, less stable. However, the less stable can be formed through less steric with a low activation energy. With the more steric, but you can get the more stable product. So we call this case thermodynamically favored. So thermodynamic controlled product. This product is not as stable, so usually you don't form as much, but because the activation energy is low, kinetic is favored for forming this guy, so we say kinetically controlled product for this case. So this case is when you have a less steric, and this is the case where you have more stable product. So basically you are dealing with these background energy in the reactions. So let's get back to the reaction. This is tricky. When you have, let me see, Br is in, H is out, so if you do Rs, it is R, right? So this R configuration, 2-bromobutane reacting with, say, water and unknown condition, and you got this. So what mechanism is it? You got the racemic mixture, so this must be SN1. So this can, cause some other questions. What if you only got this? So, R gave you R. That's only possible when you do SN1. SN1 gives us, R and the S, so you can have a R from the R. But if you do SN2, you only get inverted configuration, so you should get S only. So this is only possible from SN2. That's only possible from SN1. And these are together possible from also SN1. This is a tricky situation. Say you got this reactant, secondary brominated compound, and say you are getting this mostly. So what type of the reaction would that be? Well, this is a substitution, so you can think of it as a SN1 or 2, but when you remember SN1, out of this making secondary carbocation will rearrange to the tertiary, so your nucleophile will end up here, not there on the secondary, so that's not SN2, SN1, so it must be SN2. Therefore, you need strong base, but you cannot choose a base because base is sitting right there. So that's best SN2. if you're worried about the secondary reacting with the 2 carbon, I mean, that's a really good question. So then maybe the best choice for you is to drop temperature, make it cold, so you can get the most SN2 out of it. And if you got this, then you know SN2 is possible out of this, but also E2 is possible. So in order to get this, you have to also think of avoiding this E2, Hoffman, Zaitsev. So you use somewhat big base like ethyl group or isopropyl group, but this time you need, not cold, I'm sorry, you need some heating, because heating is helping elimination. So then you can get this as product selectively. For this, you need to use even bigger base. And for elimination, heating helps. Also, you can think of this kind of selectivity situation. What if you have 2 same chlorines that will be same energy product, and you have isopropyl, very big, so it doesn't allow the ring flip, because then it will go to the axial, and that's very unstable. Therefore, the structure, the conformation of the ring is fixed. So when they give you this type of condition, which hydrogen do you react with? So you're going to form double bond here, because the secondary has 2 carbon nucleophile that's strong, and you have a heating going on. So it's slightly over the borderline of a steric hindrance for SN2 versus E2. So the beta hydrogen, in this case, these two or these two. So let's restrict our discussion on these two. Which hydrogen is going to react and which chlorine is going to react? Let me label as a chlorine A and the chlorine B. The rule for the E2, the hydrogen and the leaving group, you should select those are on the same plane. Whether it's anti or syn, doesn't matter. But it must be on the same plane in order to form double bond. So as this try to attack, say, this hydrogen, this will be pulled away, and then you are forming pi bond there. I'm sorry, p orbital there, and that should be overlap with the p orbital that's formed by the leaving group departure. So here you lose this leaving group here, then you're having p orbital there, so they're able to form pi bond. If you pull off this hydrogen, hydrogen leaves p orbital this direction, so this doesn't overlap with this chlorine p orbital, that chlorine bond p orbital, none of them, so it's not possible. Therefore, you know HA will be selectively reacting and the ClB is going to be selectively reacting. Then you form double bond here, right there. That's sp2, not sp3. Therefore, your drawing has to be this way. Then you have your chlorine sitting there, and there you have your isopropyl group. All right, more selectivity. So then you can think of addition. We just did a couple videos. How do you put any type of nucleophile, OH, halogen, even things like this acetate, a lot of different things. How do you put nucleophile there? Selectively, not here. Well, then, this is Markovnikov, so you need to give a little catalyst and giving hydrogen a bond there, making this carbon being positive. Then nucleophile will be attacking there, top and bottom, racemization possible, and you get the connectivity regioisomer there. The other regioisomer, anti-Markovnikov, putting nucleophile there, any type of nucleophile, is anti-Mark. So you can directly put there, but there are only two options. You can put OH or halogen. If you want to put something like that, that's not possible directly. So you have to first make this, then replace hydrogen with the group acetyl group, or you put the halogen there in anti-Mark addition, then you get this one replacing the halogen, then you get this nucleophile sitting there. Remember, there are only two types of anti-Markovnikov addition in your textbook, usually for sophomore organic chemistry. So if you have to add other than OH and the halogen, then you have to go through them to put whatever you have to. Let's get another piece of paper. A couple more entries from earlier videos about selectivity. Well, when you have double bond like this, how do you add something, something in the double bond as a syn or as anti? Say you can add hydrogen as a syn, right? And you cannot add hydrogen as anti to the double bond. We were able to do it to the triple bond. You can add hydrogen to make alkene as a syn. Also make alkene as a trans. There you use Lindlar catalyst. There you use a sodium metal in the liquid ammonia. Okay, for double bond, having two things as a syn, we had hydrogens, H2 addition to it with a catalyst. And also we had borohydride case where we add anti-Markovnikov addition of OH as a syn. So one hydrogen and the OH will be added as a syn. There could be some consequence of the stereochemistry if you do syn addition. Not always, but you need to remember that for a certain case. And also osmium tetroxide in the oxidation gave you two OHs as a syn, and the KMNO4 in cold temperature also gave you OHs as a syn on 1,2 carbon. Then the anti-addition, you had the Br2 making non-traditional bridged intermediate and gave you trans or anti-addition. Then you had a halogen like a chlorine or bromine bound to the OH. They, halogen and OH, added in anti-fashion. Also, you could add OH in the anti if you use MCPBA first, make epoxide, then you are using either H3O plus, the acid, or you can use OH minus to make the 1,2 anti-diol. And last, lately we had the selectivity of oxidation. We could oxidize up to diol, or we could oxidize two carbonyl groups, or we can choose to oxidize selectively to all the way to the maximum oxidation state. So the diol was possible with the osmium tetraoxide, or you could do it just like we said a couple seconds ago, potassium permanganate in cold condition, then splitting the double bond, giving 2 carbonyl, but not the maximum oxidation state. You could have still aldehyde, surviving if you do ozonolysis, but quenching it using zinc and copper amalgam, or sulfides, any type of sulfides. Well, if you want to choose selectively go all the way to the maximum oxidation state, you don't need to do this, right? You just treat it with the ozone, one option, and the other option you can do it with a potassium permanganate with the heating. So that's just summarizing the aspect of the selectivity and the reactivity of the reactions so far we have covered, but there are a lot more reactions to be covered, and it will be mentioned in terms of selectivity, but you need to spend time to organize them separately in terms of selectivity. So hopefully this again is helpful for you, and we are ready to move on. See you next time.